All right. Can everybody hear me okay? Awesome. Thank you for joining us. I'm excited to have you guys here. Um, I'm here to talk about a new mode of multiplayer that we've been working on at Tashi. Next slide, please. Uh, I'm Ken Anderson. I'm the CTO of Tashi. And what we've been focusing on is a consensus algorithm based transport protocol for gaming. So that's kind of the high level. To give a little bit of a background, I come from the distributed ledger and cryptography space, and while gaming and Web3 haven't been super successful so far, what we've noticed is that a lot of the technologies under Web3 has received a lot of attention and innovation, and we saw that there was some opportunity to take some of that consensus, the best consensus algorithms from there, and use it in real-time gaming. And so what we did is a few years ago, we went ahead and rewrote one of the best consensus algorithms out there. We rewrote it in Rust so that it would actually be as close to the metal as possible and we could deploy to multiple architectures instead of the Java implementation that it originally was, which would have been untenable for gaming. And we ran through a bunch of tests. We did a proof of concept, and I'll actually show you our proof of concept here. We took the boss room demo. Some of you are familiar with this from Unity. They've got their boss room demo for multiplayer, kind of showing how to use netcode for game objects. And we took that and we said, okay, can we actually have a game running on top of a consensus algorithm? That's the real question. Can we take this technology that we've learned from and that has really matured and developed in this Web3 distributed ledger space, and can we take that same technology and use it to play multiplayer games? And as you can see from our proof of concept, when we originally did this, we were able to get pretty great performance. Now this is running on localhost, so it was a proof of concept for us to figure out, can we even use consensus algorithms to support the backend for gaming as a network transport layer. So we went ahead and in addition to doing our proof of concept and going, okay, this works on localhost, we need to develop this and we need to test it out in the wide area network. So we did a little bit of a game jam, and there's a team that came out and they basically developed this very simplified game in a few days at our game jam that was running on the wide area network. And this is 4 players at different locations in the world playing this multiplayer game with them, and we don't have any servers. We don't have any relays. We don't have a host. It's a consensus algorithm driving all of that. So this is why we call it a new mode of multiplayer. We're getting to the point now where all of the nodes become hosts, and the server part of their host are synchronizing with each other. And we'll talk a little bit about the consensus algorithm itself. But it's pretty exciting to see like people adopt our tech and actually make it work in a little game jam. So let's go ahead and talk about the different multiplayer modes. We've got the dedicated server model, which many of you are familiar with. In this model, the network architecture is very simple. The server itself is authoritative, supports things like state transfer, state sync, style game development. The negative side, kind of the challenge in this space, is really the cost. One of our dev studio partners we talked to said that as much as 40% of their entire revenue goes just to the egress cost from their servers. And so that's one of the challenges of this particular architecture. We also have what some people call peer-to-peer. It's a host-client model where one of the peers becomes the server. And in that scenario, we've got a few things going on. It's a lower infrastructure cost, so you get to reduce some of that egress cost that one of our partners was talking about. But you also have a little bit of network complexity you have to deal with. The host itself is authoritative, so in these scenarios, the host can sometimes manipulate the state, or often manipulate the state. I remember back in my Call of Duty days, earlier in the early Call of Duties, people would join and leave game sessions until they could guarantee they were the host, and then it was like wall hacks and aimbots on. And so there's that challenge of dealing with cheating in the host-client architecture. So you got that kind of going on there. Then we have like this peer-to-peer architecture that has come out recently in the last, I would say in the last 10 years, what I mean by recently when it comes to network architecture. But often it requires a relay still. Sometimes that relay still needs to be authoritative. It does lower infrastructure costs even more, but it also increases the network complexity. And it often requires that authoritative relay anyway. So now the question is, why don't we just use a dedicated server or some minified version of that authoritative server? So what we've developed is something that we're calling mesh multiplayer mode. And in this scenario, it's just the peers. And we'll talk a little bit about fault tolerance too. There are scenarios where we can leverage servers for intermittent fault tolerance, but not as the main multiplayer mode. But some of the advantages we have with this is it's really low infrastructure costs. And I say here, you'll see that 2/3 of the players are the authority. Because we're using a consensus algorithm, what we're doing in essence is we're having all the players pass messages to each other, and when 2/3 of the players have witnessed it, and we can do this we can prove this mathematically, then we'll say that that message is valid, and now everybody can execute it. We'll talk a little bit about how that flow works in the game cycle. But what this in essence does is it actually kind of inoculates a couple types of cheats. One of them is like the lag switcher. So the lag switcher is increasing their latency temporarily to give themselves an advantage in the game, whether they're trying to rubber band around the game or whatever it may be. But in this case, what happens is all they're doing is ostracizing themselves from consensus. So the game continues to run because the fastest 2/3 are responsible for deciding the flow of messages. So if you're lag switching, all you're doing is giving yourself a disadvantage in this model. So we've kind of helped to mitigate some of that risk. Another type of cheat that we kind of inoculate a bit against is the host local state edit cheat. So while you still have access, everybody has access to the state of the game, nobody can manipulate the state of the game without everybody else detecting it in this model, because we can check hashes and we can replay the stream of messages that have reached consensus between each other. So those are the two types of major cheats that we have an advantage in, that help in. You get kind of like a lot of the benefits of a dedicated server with some of the costs of a peer-to-peer network. Now, the challenge is, full transparency. The challenge is I like to be as academically and intellectually honest as possible. There is network complexity. Part of what we've been working on is NAT traversal. That's a lot of what we've been working on. And even in the demo that I'm going to talk about here in a little bit, we use Unity Lobby Service to initialize the address book that we use to start the session. So there's still a need for infrastructure. It's not that we're eliminating infrastructure completely, but the question is, in our game sessions, do we really need to pay the infrastructure and egress costs of dedicated servers for every scenario? There is a consensus latency. So there's kind of two big buckets of game types that I think about. The first one being the games that fit perfectly for what we need, that aren't latency sensitive, that would be perfect fit for this. And we'll talk a little bit about the latency in a little bit, but those that would still fit nicely because the game type isn't sensitive to latency. And then there's those where I suspect that the game developer or the dev studio is going to have to get creative with their netcode to compensate for this additional latency. And I suspect there are a lot smarter people than me who will figure that part out. But in full transparency, there is additional latency because of the consensus process, and it's not very much. But then also you have the system load. So calculating consensus is not free. We're doing cryptography. You have to generate signatures, you have to validate signatures, you have to generate hashes. So there is cryptography involved. It's a minimal additional compute cost. It can even potentially be offloaded into the GPU for certain types of functions. We're actually working on optimizing with GPUs so that we can offload some of that into the GPU so the CPU is not getting hit as much, or the game dev could decide how much they want to offload to the GPU versus the CPU. I know that in multiplayer, specifically in high graphics games, every resource, every ounce of resource is precious. So we've worked really hard to minimize that footprint. So let's talk real quick about how it works. So we'll start with the consensus. The first thing in our consensus protocol, there's really two major phases in the consensus protocol. The first one is this gossip about gossip stage. And in this case, we're gossiping. Many of you are familiar with gossip protocols. It gets information out quickly to all the parties in the session. But we take it a step further. Not only are we gossiping the messages that we are generating and the messages that we're receiving from other players, but we're also gossiping how we learned about that information. So we're adding 2 additional hashes to that message that points to the last 2 messages that we've talked to or that we've received, which allows us to generate a graph of these messages. And it's a directed acyclic graph, meaning directed, it's all flowing in one direction through time. Acyclic meaning that none of the future messages have historical messages as children. So that's only as ancestors. And so it's a directed acyclic graph. Once we've created this data structure of a DAG, then we run our algorithm, which is a virtual voting algorithm. And I say virtual voting because the most sure way, the most final way to reach consensus is for me to just reach out and say, everybody raise your hands and let's vote on something, right? And then we count up the votes and we go, okay, cool, we have consensus. But voting like that over a network between decentralized computers is very hard. It takes a lot of messages. It takes at least 2 extra messages to come to consensus, because not only do you have to pass the vote, somebody has to tally the vote, and then they have to pass that message back of the result of the vote. So we've got at least 2 messages in that process. Virtual voting doesn't require that. As we're passing messages, because of this gossip about gossip, because of that dual parentage relationship of every message, we now can look back and calculate what other people would have voted. In other words, what we're trying to determine is, has 2/3 of the network seen this message? And we can do that by looking at the flow of the message in question and how it's connected to other messages in this DAG. Okay, I hope I haven't lost anybody. I'm kind of down in the weeds now. But fundamentally, what this gives us is it basically gives us a decentralized message queue, if you will. So if you see, this is like a message queue. You've got multiple players. Each player is passing messages into this consensus algorithm by recording it locally and gossiping it out. And then the consensus algorithm is responsible for ordering the messages so that everybody executes those messages in the same order. So you can think of it like a message queue. But we get a fair timestamp for each event, which might be valuable for some of you if you want to know how one event, what time it happened relative to another event. It's not an accurate, atomically accurate timestamp. It's a relative timestamp, meaning that the network itself, the question is, how long did it take for this message to be seen by 2/3 of the network relative to this other event? So if the question is, did I pull the trigger before you moved? And we know from that distance, it should take 4 milliseconds for that bullet to travel and impact that player. But you pressed the button 3 milliseconds before I pulled the trigger, then we know that you did not successfully dodge that bullet. Does that make sense? We can mathematically look at it and go, based off this message queue, we can do some fun math about calculating how we resolve conflicts in the timings between how players interact with each other, because you get this fair timestamp. That's a really crazy, powerful thing that I'm not going to spend a lot of time on, but I can see some of the wheels are turning in some of your heads about how that could be used. Fair consensus ordering of events. Again, did this happen first or did that happen first? If we've got timestamps, it's trivial to generate an order, right? So now we've got this fair sequence. Like I said, it basically becomes a decentralized message queue. All the players become party in this message ordering via consensus algorithm. Okay, I'm going to go really quick through this part. This is just taking a quick look at Unity. In our Bostrom demo, this is basically what we did, is you went in and we imported the lobby and netcode for game objects packages into Unity. Then we imported the Tashi Network Transport, which is a package that's ready for Unity. Tashi Network Transport, TNT. It's kind of a fun name. You can go to our website and download it, import it manually right now. We're planning to submit it to the asset store once we hit our version 1, and then we'll be able to just pull it from there. But once you've got that in there, then you just go down, when you set up your network manager, you go down and you just swap the transport to the Tashi Network Transport. And then what we got to do is, now that we've got the network transport package installed and kind of set up in our network manager as the transport, we now have to configure our address book. And so it kind of looks like this. As a player, I've got this address book that tells me who I'm talking to, IP addresses, routing information, public key information, so that I can now validate everybody else in the network. So what I'm going to do is I'm going to talk to the Unity lobby using the key value store in Unity lobby. I'm going to initialize the lobby. I'm going to send my outgoing session details. So here's my IP address. Here's how you talk to me. Here's my public key. And then I'm going to receive all the incoming session details from everybody else who's in that lobby. So all the other players in that lobby. And then we have update the session details. And then we can just connect to the transport and use netcode for game objects like we would with any other multiplayer game. Okay, so if you've done that before with multiplayer, all we're doing is replacing the network transport. There's not a whole lot you have to do beside that. There might be some optimizations you can do about how the address book is handled, but beyond that, you're just playing multiplayer at this point. This is kind of what the code looks like, importing the network transport. We're initializing lobby. We are sending out our outgoing session details into the lobby. If we're the host, we're also initializing the lobby. By the way, we don't really have a concept of host, but Unity does. So we kind of have to like fake that. So the first person to create the lobby is really the Unity host. And And then you go out and you grab all the Unity or all the lobby details from all the other players, all the session details from the other players, and generate your address book. So once you've done that and you've updated your session details, you're off to playing the game. To give you an idea, I talked about our one dev partner who says that 40% of the revenue is just going out to egress. In that scenario, we predict that they are going to be saving up to 80% of their infrastructure costs just by using this transport. We've got over 1 million game events, significantly more in certain optimizations, but we've got more than 1 million game events being synchronized per second. And we're looking at about 30 to 50 milliseconds average. Sometimes we get up to a high of about 100 milliseconds. Gives you an idea of like what kind of games cleanly fit into this category of mesh multiplayer and what kind of games might need some massaging in the netcode to work with it. All right, so that's everything. This is kind of our coming out of stealth presentation. What we're really looking for right now is engagement of helping us understand how we make this fit your use case, right? This is our product market fit phase. We want to engage with you. We want to get your feedback. We want your criticism and telling us what's working and what's not working so that we can hone in and fix the things that are important to you. So with that said, I'm going to thank you very much. You can scan this gigantic QR code on the screen, and this will take you to our Discord server, specifically the links channel, where you can have download all of our SDKs, our documents, and all that stuff. Thank you very much. Very good. Okay. Why don't we jump to questions? I'll go ahead and leave this on so I can hear myself and you. This is good volume.
Hello, hello.
Hello.
Hey, thank you. Great presentation. Very interesting concept. I was wondering if everyone is talking to everyone, how does this scale when you get a larger amount of players?
That's an excellent question. So we've tested at 48 players pretty consistently, and it's worked beautifully. 16 players is kind of the sweet spot. That's where we see almost no degradation relative to smaller numbers, but also the most number of players involved. But yeah, I mean, when I showed the milliseconds, 16 players is what we capture that data at. 48 players, that obviously is going to go up a little bit. I think we got at a high of 200 milliseconds with 48 players. So now when you get to bigger levels, the question is, how big do your sessions really need to be, and can you kind of do phasing to support multiple concurrent sessions that players can move from one session to another? I suspect there's a lot of magic that happens at big studios that I don't understand that would make this work at scale. But yeah, ideally, if you want to talk about like the perfect ideal game type, it's like limited session, 16 players, casual gaming. Yeah, well, minimum 4 players actually. Yeah, so the math, it's wonky. Like 3 players is true is what you need to get 2/3 consensus, but 4 players is what you need to allow one person to fall out and still get consensus. So, but let me add to that a little bit. I talked about before having kind of that the fault tolerance and failover strategy. Something we're working on is setting up Tashi relays that only get invoked when you get down to the levels where it would be detrimental as players drop out. And if they drop out, then the Tashi relays would jump in as fill-ins for the consensus purposes only. So we're talking about how to smooth that out and handle that from an infrastructure perspective. But still, the vast majority of your game session is happening between the players, and it only becomes invoked when you get to those lower levels, like say sub 5 players. Excellent question, though. Thank you. Any other questions?
Hello. So what you described really reminded me of the Avalanche's snowball consensus algorithm, and you've mentioned that your quorum is like 66% of the players, right? So I'm wondering how many rounds of consensus are you running, and what is your certainty threshold for the consensus algorithm?
Okay, so you asked a few questions in there. It's based off of the Hashgraph algorithm. It's loosely based off the Hashgraph algorithm, not the Avalanche. Which is a mathematically final asynchronous Byzantine fault tolerant algorithm, ABFT. It does take 4 rounds to calculate the median timestamp, because not only do you have to have one more round that witnesses the events, but you have to have 2 rounds to strongly see and validate that those rounds saw the events previously. So it takes 4 rounds, but despite all of that, our latency is 30 to 50 milliseconds. So you can imagine the rounds are significantly faster. But that's an excellent, very low-level question. I appreciate it. Over here. We have one more, and then we're going to cut it off? Okay. Thank you very much. If you have any questions, We've got a bunch of Tashi guys sitting around here. Most of them have Tashi hats. You can come chat with us. I'm going to step off to the side here a little bit, so if you got additional questions, we can answer that. Thank you very much.